Have you ever really stopped to think about how we describe something as simple as, well, movement? It seems pretty obvious, right? But in physics, being precise is everything. So today, let's get super precise and break down the basics of motion, speed, and velocity.
Okay, think about it. Right now, you probably feel like you're sitting perfectly still. But you're on a planet that's spinning on its axis and rocketing through space around the sun. So are you moving or are you not? The answer, and this is kind of wild, is it depends.
And that, right there, is the first huge idea we need to lock down. Motion isn't some absolute thing. To describe it at all, you first have to decide what you're measuring it against. We call this a reference point or an origin.
So this brings us to our first key idea, and trust me, it's the foundation for everything else we're going to talk about. To describe motion, we first have to agree on a frame of reference.
This is the perfect example. If you're on a bus, your reference point is the bus itself. And from that point of view, it really looks like the trees and buildings are moving backward. But if you're standing on the sidewalk, your reference point is the ground. And obviously, the bus is what's moving forward. It's the same event, but two totally different descriptions, and both of them are 100% correct from their own perspective.
All right, now that we've got our reference points sorted, let's talk about the journey itself. Because it turns out there are two very different ways to measure a path, and you've got to know the difference. First up, we've got distance. This one's the easy one. It's just the total amount of ground you covered. Think of it like the odometer in a car. It just adds up every single meter you travel. It's just a number, a magnitude, like 10 kilometers. In physics, we call that a scalar quantity. So let's imagine a little trip. An object travels 60 kilometers out, then it turns around and comes back 35 kilometers. So what's the total distance? Well, just like your car's odometer, you just add it up. 60 plus 35, that gives us 95 kilometers. Simple enough, right? But then we have displacement. And this is a whole different beast. See, displacement doesn't care about the scenic route you took. All it cares about is the straight line shortcut from where you started to where you ended up. And, this is key, it always includes a direction. We call that a vector quantity. So let's go back to that exact same journey, all 95 kilometers of it. What's the displacement? Well, you went 60 out and 35 back, so you ended up only 25 kilometers from where you started. That's it. That's the displacement. It's the net change in your position. And this is where it all clicks into place. Distance tells the story of the entire path you took. It's a scalar. Displacement, on the other hand, just tells you the outcome, the shortest path from A to B, making it a vector. Now, this leads to a really cool, kind of mind-bending idea. Imagine you run a full lap on a 400-meter track. You've definitely traveled a distance of 400 meters, right? But because you end up in the exact same spot you started, your displacement is 0. Okay, so we've covered the where. Now, let's add the when. As soon as we bring time into the picture, we get to upgrade our descriptions from just distance and displacement to speed and velocity.
Average speed is pretty much what you think it is. You just take the total distance you traveled, that whole winding path, and you divide it by the total time it took you. It just tells you, on average, how fast you were covering ground.
Let's run through a quick example. Say an object travels 16 meters and it takes 4 seconds. Then it travels another 16 meters, but this time it does it in just 2 seconds. The total distance is 32 meters, and the total time is 6 seconds. So the average speed is just 32 divided by 6, which comes out to about 5.33 meters per second.
Velocity, on the other hand, is the partner to displacement. Its formula is your displacement divided by the time it took. And this is the crucial part. Velocity isn't just about how fast you're going, it's about how fast you're going and in what direction.
And really, it all boils down to this simple difference right here in their formulas. Speed is built on the total distance, while velocity is built on the net displacement. It's a tiny change in the formula, but it makes for a huge difference in what it actually means.
So let's tie all of this together. I've got one final example that I think makes the difference between speed and velocity just perfectly clear.
So, meet Usha. She's swimming in a pool that's 90 meters long. She swims from one end to the other and then immediately swims all the way back. So she covers a total of 180 meters. And the whole thing takes her exactly 1 minute. First question for you. What was her average speed? Just remember that formula. It's the total distance divided by the total time. Well, her total distance was 180 meters and her time was 1 minute, which is 60 seconds. So 180 divided by 60, that gives us an average speed of 3 meters per second. Not bad. She was moving pretty fast. Okay, but here it is.
This is the key question. What was her average velocity? Think about its definition. Displacement divided by time. 0. Her average velocity was 0 meters per second. But how? Well, because she finished her swim in the exact same spot where she started. Her total displacement was 0. And if your displacement is 0, your velocity has to be 0, even though she was actually swimming at a good clip.
So let's just quickly recap the big ideas. Number 1, motion is always relative to something. Number 2, distance is the whole path you travel, while displacement is just the shortcut from start to finish. And finally, that exact difference is what separates speed from velocity. Speed is just how fast, but velocity is how fast and which way.
And that leaves us with one last little puzzle to chew on. If velocity includes direction, and any change in velocity is something we call acceleration, then how is it possible for an object to be moving at a constant speed but still be accelerating? We'll just leave that one right there for you to think about.